Yes, children. Now let us see what is meant by metal deficiency defect. Okay, metal excess defect and metal deficiency defect under non-stoichiometric defects. Okay, now let's see metal deficiency defect. Now here what happens, say for example, this is a crystal lattice which is made up of M plus and X minus, just like NaCl मान लो, ठीक है, anything like that. M plus and X minus, this is forming a crystal lattice. Now what happens is, from this crystal lattice, two M plus ions leave. They leave the lattice. When they leave the lattice, the place where they were, they are all now vacancies. They are now vacant. Now, say for example, if an impurity is added, not exactly an impurity I should say, the same metal, if it is exhibiting itself in a higher charge, then what happens? Say in the case of Fe, Fe can exist in the form of Fe2 plus as well as Fe3 plus. Is it not? So, the metal in a particular oxidation state, it is now replaced by the same metal in a higher oxidation state. जैसे M plus is replaced by M2 plus. So here when two M plus ions leave, two positive charges are leaving. And two positive charges have come now in the form of the same metal in a higher oxidation state. Okay, so two positive charges have come inside, but one vacancy is there. The same metal ion is having two positive charges, which is compensating or which is balancing the electrical neutrality. So there was no need for another metal ion, then positive charges will become excess, is it not? So this 1 M2 plus can replace 2 M plus and there is one vacancy created, right? Now, how many ever charges, the increase in charge is going to decide the number of vacancies. Now this particular defect is shown only in transition metal compounds because transition metals, they have the capacity to exhibit themselves in variable valency. You have studied D block elements. They show variable valency, they show multiple oxidation state. Only in such compounds this particular defect has been found. Now, what I have written, see, it occurs when a cation is missing from its lattice site and a cation of higher charge gets accommodated, maintaining electrical neutrality. Right? Now this is shown by transition metal compounds in which transition metal ion exhibits variable valency. Right? Okay, now how many ever M2 plus enters, that many vacant sites are created. Say M plus is leaving, two M plus ions are leaving and one M2 plus is taking entry and one vacancy is created. Is that clear? So how many ever M2 plus, in this particular case, how many ever M2 plus enters, that many vacant sites are created. Right? Now say for example, if you are using FeO, here what happens, some of the Fe2 plus ions are replaced by Fe3 plus ions. But electrical neutrality is always maintained. So here you can take an example of, if 3 Fe2 plus ions are leaving the site, then it will be replaced by 2 Fe3 plus ions and one vacancy will be created because 3 into 2 is plus 6. 2 into 3 is again plus 6. Okay, so electrical neutrality is maintained. Plus 6 चला गया, plus 6 आ भी गया. ठीक है? Here there were 3 Fe2 plus ions. Now that is replaced by 2 Fe3 plus ions. So there will be one vacancy created. The site of one Fe2 plus will be left vacant. Okay. Now because of this defect, what has been found is the composition of a particular compound. It changes. Say, if you say FeO, it is supposed to be in the ratio of 1:1. But it is never 1:1, because in this FeO lattice, some of the Fe2 plus ions have been replaced by Fe3 plus ions. Okay, so the chemical composition has been found to be Fe 0.95:1, O1. Is that clear? It is not equal to 1:1. It is changed. Okay, because of a higher valence state replacing the lower oxidation state ions. Right? Now we have impurity defects. Now this impurity defects it can exist or it can be shown in ionic solids as well as in covalent solids. When you want to explain in ionic solids, how does it arise? It arises when a foreign atom is present in the site of the host atom. Host atom की जगह पे कोई और atom आ गया, तो this is called as an impurity defect. Host atom is different and the impurity atom is different. In the previous case, metal excess defect में क्या देखा था? The same metal in a higher oxidation state is replacing the lower oxidation state ion. Okay, here it is an impurity atom, totally different. Now say for example, if SrCl2 is added in NaCl lattice, so the entry of one Sr2 plus will force two Na plus ion out. This is Sr2 plus having two positive charges. So if two positive charges are coming inside, then two positive charges should go out. Okay, but Na is possessing only one positive charge. So two such ions will leave the lattice in order to compensate the +2 charge by Sr2 plus. Okay, so in NaCl crystal lattice, presence of Sr2 plus ions as impurity, it creates vacancies. तो एक Sr2 plus एक Na plus की जगह पे बैठ गया और दूसरी Na plus की जगह खाली हो गई. So it will create vacancies. Right? So entry of one Sr2 plus into NaCl lattice forces two Na plus ions out. In the place of one Na plus, Sr2 plus is accommodated and another Na plus site is left vacant. Right? Now these vacancies make them as good conductors. Okay? Like that you can also explain in terms of addition of cadmium chloride CdCl2 in AgCl lattice, where CdCl2 is the impurity and the host lattice is AgCl, same as the kind of NaCl and SrCl2. Okay, so this is also in the case of ionic solid. Now let's come to covalent solids. Now this is a very interesting concept. In covalent solids, say for example, you take silicon lattice. Now this is your silicon lattice. Silicon is tetravalent, carbon is tetravalent, carbon, silicon, germanium, they all belong to the same group. They are all tetravalent atoms. Now this is the network structure of silicon, where silicon is surrounded by 4 other silicon atoms. Okay, now you are adding an impurity. Right? Now this impurity atom, now silicon belongs to 14th group, and the impurity atom that you are adding, it may belong to either 13th group or it may belong to 15th group. Okay, now let us first discuss that we are taking an impurity atom from 13th group. What are the elements present in 13th group? Boron, aluminium, gallium, indium, thallium. These are all the elements present in 13th group. Boron, aluminium, gallium, indium, thallium. Now any one of this if it is added as an impurity. Now that impurity atom has replaced the host silicon atom in one place. Okay, and it is having a valency of 3 only. It's having only 3 valence electrons. So when it is incorporated, or when it is getting itself accommodated in the place of silicon, only 3 valencies it can satisfy, and the 4th valency of silicon, like here it has to share with 1 more electron. That electron is not there with boron. It is having only 3. It is sharing with the other 3 silicon atoms. There is no 4th electron with boron. So इस सिलिकन के साथ शेयर करने के लिए बोरॉन के पास इलेक्ट्रॉन है ही नहीं. So as soon as that this silicon feels that I don't have a companion, boron cannot provide me an electron, what happens is the adjacent silicon atom, its electron, it moves towards the vacant space associated with boron, and this electron, when it travels here, it will satisfy these two. It will satisfy this silicon. Now when this is transferred, this part will become an electron hole. Now immediately the next silicon, the electron of next silicon will pass on to this hole. So in quick succession, when you see the electron holes, from here it is now here, from here it is now here. So the whole movement is moving from right to left, and the electron is shifting this way, is it not? So electron movement is shifting this way. You know very well that the electron movement and the charge, they move in opposite directions. Okay, so that is what is indicated here. Whole movement is from here to here, and electron movement is from here to here. Okay, now this addition of impurity into the whole host lattice and improving a particular property is called doping. Okay, now silicon becomes a conductor, otherwise it was an insulator. It was an intrinsic semiconductor because by heat or by increasing the temperature, it could be made as a conductor, but it was showing very poor conductivity. But by introducing this impurity atom, or by doping process, it has become a semiconductor. It is much more useful.